Preparing for a software engineering at Cloudflare interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a globally distributed rate limiter for Cloudflare's edge network? I would use a token bucket at each edge location, replenishing tokens at a configured rate and rejecting requests when the bucket is empty. Local enforcement keeps latency low, while periodic aggregation provides approximate global limits. For strict quotas, I would partition counters by customer and coordinate through a strongly consistent regional service, accepting higher latency. I would also define fail-open and fail-closed behavior explicitly, monitor synchronization drift, and protect against key cardinality attacks. While answering, cover token bucket or leaky bucket algorithms, edge local versus globally coordinated state, Redis or durable storage, consistency, fail-open behavior, hotkeys, and latency-sensitive request processing. Question 2. Explain how DNS resolution works, and describe how you would build a reliable authoritative DNS service. A resolver follows delegation from the root through the TLD to the authoritative nameserver, then caches the response according to its TTL. I would run authoritative servers across many Anycast locations, replicate zone data reliably, and support UDP plus TCP fallback for large responses. Health checks would withdraw unhealthy routes. DNS changes need versioned distribution and rollback. I would also enforce response size controls, rate limits, DNS SEC validation or signing, and continuous observability. Make sure to cover recursive versus authoritative servers, delegation, record types, TTLs, Anycast, UDP and TCP fallback, caching, propagation, health checks, and protection against amplification and cache poisoning attacks. Question 3. What are the key challenges in building a high-performance HTTP reverse proxy? The proxy must handle many concurrent connections without exhausting file descriptors, memory, or backend capacity. I would use an event-driven architecture, connection pooling, bounded buffers, and explicit backpressure. TLS termination and protocol negotiation should be efficient, with HTTP 2 multiplexing and HTTP 3 considered where useful. Timeouts prevent stuck requests, while retries require idempotency checks. Caching and health-aware load balancing reduce origin pressure. Metrics should expose latency by phase, errors, saturation, and cache status. In your answer, discuss connection reuse, buffering, backpressure, TLS termination, HTTP 2 and HTTP 3, caching, timeouts, retries, load balancing, observability, and avoiding head-of-line blocking. Question 4. How would you design a CDN cache invalidation system? I would assign every cached object a deterministic key and maintain an index from purge tags to object keys where feasible. A purge request would receive an idempotent operation ID, enter a durable queue, and fan out to edge locations. Edges acknowledge completion, with retries and dead letter handling for failures. During propagation, stale content may briefly remain unless the customer chooses stronger guarantees. I would authorize purges carefully and expose regional completion status. Be sure to mention cache keys, purge by URL or tag, propagation latency, fanout, retries, idempotency, stale content, regional failures, authorization, and the trade-off between immediate invalidation and operational cost. Question 5. How would you detect and mitigate a distributed denial of service attack? I would detect anomalies using per prefix, protocol, geography, endpoint, and behavioral baselines rather than relying only on total bandwidth. Anycast distributes volumetric traffic across edge sites, while stateless filters drop malformed packets cheaply. For application attacks, I would combine rate limits, bot signals, and adaptive rules. Mitigations should begin in monitor mode when possible, then escalate automatically with customer-specific exceptions. I would track attack traffic, collateral blocking, mitigation latency, and recovery. Focus on volumetric, protocol, and application layer attacks, traffic baselines, edge filtering, anycast absorption, rate limiting, fingerprints, false positives, customer-specific policies, and safe, observable mitigation rollouts. Question 6. What is the difference between a process, a thread, and an asynchronous task? A process has its own address space and provides strong isolation, but switching and communication are relatively expensive. Threads share a process's memory, making communication efficient while introducing races and synchronization risks. An asynchronous task is usually a lightweight unit managed by an event loop or runtime. It yields during I/O instead of blocking a thread. I choose asynchronous tasks for high concurrency network workloads, threads for suitable parallelism, and processes when isolation or CPU scaling matters. Cover memory isolation, scheduling, context switching, shared state, synchronization, event loops, I/O waiting, CPU-bound work, failure boundaries, and how the choice affects performance in network services. Question 7. How would you investigate a sudden increase in latency for requests passing through an edge service? First, I would verify the increase using P50, P95, and P99 metrics segmented by region, protocol, endpoint, and customer. Then I would decompose latency into queuing, TLS, proxy processing, network, and origin time using traces and logs. I would compare healthy and affected locations and inspect CPU, memory, connection pools, packet loss, and deployment history. If a recent change correlates strongly, I would roll it back safely, preserve evidence, and then reproduce the issue. Make sure to cover symptom confirmation, percentile metrics, request decomposition, recent changes, saturation, dependency health, regional comparisons, tracing, controlled rollback, and distinguishing edge, network, and origin latency. Question 8. Design a multi-tenant feature flag service for edge-deployed applications. I would store versioned flag configurations centrally, validate them before publication, and replicate immutable snapshots to edge locations. Requests would read from memory, keeping evaluation local and fast. Rollouts could target tenants, regions, attributes, or deterministic percentage buckets. Every change needs authorization, an audit record, and a reversible version. If replication fails, edges continue serving the last known good snapshot. I would define conservative defaults and monitor evaluation errors, propagation lag, and exposure percentages. Discuss tenant isolation, low latency reads, versioned configuration, rollout percentages, consistency, edge replication, authorization, audit logs, failure defaults, schema validation, and safe rollback procedures. Question 9. Explain eventual consistency and describe when it is acceptable in a distributed Cloudflare service. Eventual consistency means replicas may temporarily disagree but converge after updates propagate. It is appropriate for configuration distribution, analytics, cache metadata, and abuse signals where small delays are tolerable. I would attach versions or timestamps, make updates idempotent, and define conflict resolution explicitly. It is not suitable for billing balances, unique resource allocation, or security changes requiring immediate enforcement. The key is documenting freshness guarantees so product behavior matches the consistency model. In your answer, define stale reads and convergence, contrast eventual and strong consistency, identify acceptable use cases, discuss conflict handling, user expectations, and situations requiring coordination or linearizable writes. Question 10. How would you implement a secure request authentication system for APIs at the edge? I would require TLS, validate a short-lived signed token or scoped API key at the edge, and keep authorization separate from authentication. Tokens should include issuer, audience, expiry, and tenant claims. Requests may include a nonce or timestamp to reduce replay. Key rotation needs overlapping validity and a secure key distribution path. Secrets must never appear in logs. I would use constant time comparisons, cache public verification keys briefly, and default to denial when validation is uncertain. Be sure to cover TLS, API keys or signed tokens, key rotation, replay prevention, clock skew, revocation, constant time comparisons, tenant isolation, least privilege, logging, and avoiding sensitive credential exposure. Question 11. What happens during a TCP connection, and how does that affect high-throughput network services? TCP begins with a SYN-ACK, and ACK handshake, then provides ordered, reliable bytes using sequence numbers and acknowledgements. Flow control protects the receiver, while congestion control adapts sending to network conditions, including slow start and retransmission. Handshakes and teardown consume latency and resources, so high-throughput services use keep-alives and connection pooling. I would monitor retransmits, handshake failures, window sizes, and port exhaustion, and consider HTTP 2 or QUIC for multiplexing. Cover the three-way handshake, sequence numbers, flow and congestion control, retransmission, connection teardown, keep-alives, slow start, ephemeral ports, and why pooling or newer protocols can reduce overhead. Question 12. How would you prevent a cache stampede when a popular object expires? When a hot object expires, I would allow one request to refresh it while others receive the previous value under stale while revalidate. A short distributed lease or local single flight mechanism prevents duplicate origin fetches. TTL jitter and probabilistic early refresh spread renewal work over time. If the origin fails, stale content can continue within a defined safety window. I would bound refresh concurrency and monitor origin requests, lock contention, stale responses, and refresh errors. Discuss request coalescing, stale while revalidate, probabilistic early refresh, jittered TTLs, distributed locks, origin protection, failure handling, and ensuring that mitigation does not create a new centralized bottleneck. Question 13. Describe a robust deployment strategy for a globally distributed service. I would build an immutable artifact, run unit, integration, security, and load tests, then deploy to a small canary region. Automated gates would examine error rate, latency, saturation, and business-specific signals before expanding by waves. Database and protocol changes must remain backward compatible across mixed versions. Feature flags separate code deployment from activation. Rollback should be tested and fast, but I would also preserve forensic data because a partial rollback can leave distributed state inconsistent. Focus on immutable artifacts, automated tests, canaries, regional waves, health signals, backward compatible schemas, rollback, feature flags, capacity checks, and handling partial failures during deployment. Question 14. How would you design a durable, high-throughput event ingestion pipeline? I would accept events through stateless gateways, validate schemas, and append them to replicated partitioned logs. Partitioning by tenant or entity preserves ordering where needed while distributing throughput. Producers receive acknowledgements only after durable replication. Consumers track offsets and use idempotency keys because at least once delivery is practical. Backpressure, bounded queues, and dead letter topics protect the system. Schema versions must evolve compatibly, and retention should reflect replay, compliance, and storage cost requirements. Mention partitioning, ordering guarantees, replication, acknowledgements, backpressure, retries, idempotent consumers, schema evolution, dead letter handling, retention, and selecting at least once versus stronger delivery semantics. Question 15. What are the main security risks of running serverless code at the edge? The largest risks are escaping the sandbox, abusing CPU or memory, leaking secrets, and using dependencies with vulnerabilities. I would isolate tenants with a hardened runtime, enforce CPU, memory, execution time, and outbound network limits, and apply least privilege permissions. Secrets should come from controlled bindings rather than source code. Dependency scanning, code signing, and audit logs address supply chain concerns. Input validation and abuse controls remain essential because trusted code can still create application layer denial of service. In your answer, cover tenant isolation, sandbox escapes, resource quotas, supply chain risks, secret management, denial of service, data residency, permissions, input validation, and auditability. Question 16. How would you choose between a relational database, key-value store, and distributed log for a new service? I start with access patterns and correctness requirements, not product preference. A relational database fits transactions, constraints, joins, and flexible queries. A key-value store suits predictable lookups, massive scale, and simple access, but requires careful key design. A distributed log is ideal for ordered append, replay, and decoupled consumers rather than arbitrary queries. I would estimate throughput, latency, growth, and failure behavior, then prototype the highest risk workload before committing. Discuss access patterns, transactions, joins, consistency, write and read throughput, ordering, retention, query flexibility, operational complexity, and selecting storage from requirements rather than familiarity. Question 17. Tell me about a time you disagreed with a technical decision and how you handled it. On one project, I disagreed with choosing synchronous calls between services because expected traffic and failure behavior made cascading timeouts likely. I documented the risks, built a small load test, and proposed an asynchronous queue with clear delivery semantics. The team reviewed both options and selected a hybrid approach, synchronous validation followed by durable events. Latency and availability improved, and we avoided a prolonged debate by using evidence. I learned to challenge ideas directly while supporting the final decision. Be sure to structure the story with context, competing constraints, evidence, respectful communication, decision ownership, measurable outcome, and what you learned, emphasizing collaboration rather than winning. Question 18. How do you approach writing reliable code for a large, mature codebase? I first map the behavior, dependencies, ownership, and existing tests before changing code. I prefer a narrow, reversible change with explicit invariants and metrics rather than a broad rewrite. New tests cover normal paths, failures, concurrency, and compatibility boundaries. I follow local conventions and ask domain owners for review. If cleanup is necessary, I separate it from functional changes. After release, I watch real signals and document any operational lessons for future maintainers. Cover understanding existing conventions, focused changes, tests, observability, backward compatibility, ownership boundaries, incremental refactoring, code review, failure modes, and avoiding unnecessary rewrites. Question 19. Given a stream of IP addresses, how would you find the top K most frequent addresses efficiently? For a manageable stream, I would count each address in a hash map, then maintain a minute heap of size K while scanning the counts, giving O and log K selection after counting. For a massive distributed stream, workers would partition by address, compute local counts, and merge candidates centrally. If memory is constrained, a count min sketch estimates frequencies, possibly with a candidate heap. I would state whether exact results are required because that determines the design. Discuss counting strategy, hash map memory, min heaps, approximate sketches for huge streams, distributed partitioning, merging partial results, ties, and the trade-off between exactness, memory, and processing latency. Question 20. How would you design observability for a critical edge service? I would define SLIs such as availability, latency percentiles, origin success, and cache effectiveness, then set SLOs tied to user impact. Metrics provide fast aggregation, structured logs capture decisions and errors, traces connect edge processing with downstream calls. Correlation IDs make investigations practical. High cardinality data needs controlled sampling and cost limits, while sensitive values must be redacted. Alerts should detect meaningful budget burn, not every transient blip. Dashboards would show regional and tenant level differences. Make sure to cover metrics, logs, traces, high cardinality dimensions, service level objectives, alert quality, correlation IDs, sampling, privacy, dashboards, and using telemetry for debugging rather than merely collecting data. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.